Okay, out of the 4 levels of Verilog modeling, switch level modeling is one which deals with the switches. So, normally we can use the transistor as a switch. So, we will deal here with instead of using BJT, we will deal with the MOSFET as a switch. So, we know that at the circuit level, normally we will use the software like PSpice in order to obtain the critical electrical calculations more accurately. If you use the PSpice and all, they will obtain the electrical calculations such as voltage, current and all accurately. Then why we have to go for the Verilog modeling? So, this Verilog modeling will be useful. So, in order to verify, this will be useful in order to verify the data flow through the network that consists of both transistors as well as logic gates. If the output of some transistor circuit is connected to some logic circuit, so a network which consisting of both the transistors as well as the logic gates. So, in order to verify the data flow through such networks, normally we will use the Verilog coding. Okay. So, basically this switch level modeling here we are going to deal with the MOSFETs. So, this explain the behavior of the MOSFETs. Okay. So, we know that if I take the n channel MOSFET, this will have 3 terminals, in fact 4 terminals, and the substrate we will not discuss here. Okay. One is called gate, another is called source, another is called drain. So, normally in order to code in the Verilog, so we will use 2 primitives. There are 2 primitives to represent this NMOS and PMOS. So, one is NMOS is one primitive, another is PMOS. The general structure of these 2 primitives is NMOS, some name, gate name, it is optional, N1. So, we have to represent out data control. There are 3 signals. Similarly, PMOS also some P1 out data control. Here normally this gate will act as a control signal CTRL, drain will act as a data and source will act as output. Suppose if we want to write a Verilog code for a simple inverter. So, we know CMOS inverter consisting of one NMOS device and another PMOS MOSFET. So, this is basically VDD two MOSFETs, this is ground, this is VDD, this is PMOS, this is NMOS, these two will be connected to the input, let input is in, and here you have to take the output out. This is PMOS, I will call as P1, this is NMOS, I will call as N1. So, the Verilog code corresponding to this CMOS inverter will be we have to use these primitives NMOS and PMOS. In addition to this, we are going to use two more primitives called as supply 0, supply 1. This is equivalent to ground. Supply 1 is another primitive normally used to represent VDD. Okay. So, in the Verilog code I am giving the module, I will give some name CMOS underscore not, only one input one output, out in. So, output is out, input is in. In addition to this, you have to give supply 0 is nothing but GND, supply 1 is nothing but VDD. Then P1, if I take this P1, so this primitive is PMOS, P1, this is optional name of the gate. So, the general structure is out, data, control. So, out is normally source, drain, gate. Okay. So, for this inverter, this is source of PMOS, this is gate of PMOS, this is drain of PMOS. Whereas, for NMOS, this is source, this is drain, this is gate. Okay. So, for PMOS P1, first you have to mention the output, which is nothing but source. Source is at VDD, so you have to write VDD, comma, then data, data is nothing but drain, drain is nothing but output, out. Then control, control is gate, which is in. At gate we are applying the input signal, this. So, this will describe the PMOS transistor. Similarly, NMOS transistor, N1. So, what is source? Source is ground, so GND. Output is drain, drain is output. In both the cases, output is taken from the drain, out, and both the gates will be operated at in only, so in. This is end module. So, this is how we can represent any of this CMOS based circuits using Verilog code. So, I will take some other gates, the universal gates such as NAND and NOR, and how to represent the Verilog code corresponding to these gates. If I take two input NAND gate, so the circuit diagram of this two input NAND gate is there will be two NMOS and two PMOS FETs. This is ground point and this is VDD point. and here the output is taken. These are two inputs. So, this will be connection is there from here to here. This is PMOS 1, this is PMOS 2, P2, this is NMOS 1, NMOS 2. So, this I will call as in comma A underscore A. This is also in underscore A. These two will be connected. This is in comma B, this input is, this is in underscore A, this is in underscore B. We have two inputs and one output. Okay. We can easily explain the operation of this one. So, for the NAND gate, the operation is, if you have in A, in B and output 0 0, 0 into 0 bar should be 1, 0 1 also 1, 1 0 also 1, 1 1 is 0. If any one of the inputs is at 0, output will be 1. Okay. If say for example, this in A is at 0, so what happens is the corresponding PMOS will be on. So, this will be in ideal case this will act as short circuit. Okay. The operation is something like this is VDD and here we have. So, this I am taking the ideal case, this will act as short circuit because in A is 0. In B say for example is 1, it can be 0 also. So, this will be open circuit, this will be off, I am drawing open circuit, this is short circuit, this is ideal case. I will discuss the practical case later. Okay. This is VDD. So, for the lower NMOS MOSFETs, in A is 0 means this will be off, this will act as open circuit and this will act as short circuit. This is G and D. So, you can see that here we are taking the output. You can see that here. So, here there is no path to connect to ground, here open circuit is there, but through this VDD it will come from this point through this short circuit. So, this output will becomes VDD, that is logic 1. Okay. So, regardless of whether both these switches are closed, if any one of the switch is closed, this is the situation, these three conditions. So, in these three conditions, so either of this one is short circuited or both will be short circuited. In any case, this will connect through this. Okay. So, here in any one of these three cases, one of this, at least one of this switch will be open circuited. So, there will be no path for the ground. And if we take the last case, if both are ones, the equivalent circuit will be, so we have something like both of these transistors will be off. So, here there will be open circuit, whereas the NMOS transistors both will be on, they will act as short circuit. So, that this path will be connected here, output becomes ground, which is 0. So, this is how we can explain the operation of two input NAND gate. So, now how to write the code correspond to this two input NAND gate. So, first we have to write down this source and drains of this NAND gates. Okay. So, this is the source, gate, drain. this is source of N2, you can call as this is gate of N2, this is drain of N2. Similarly, here these are sources for PMOS, these are drains and these are gates. Then how to write the code? I will write here itself, I will remove this. Module, I am giving the name as CMOS underscore NAND. 2 inputs, 1 output. So, output you are calling as out, inputs you are calling as in underscore A, in underscore B. Then we have output is out, input is in A, in B, then we need a wire. So, why? Because you can also think, so this terminal is already available as in A, this terminal is available as in A, in B, this is VDD, sources are VDD, VDD also we are going to define, this is ground we are defining, this also in B, this also in A. So, the only thing that is not accessible is this point, the point where the source and drain of this N1 and N2 are connected. So, this is internal connection. So, I have to define a wire, I will define this as a wire W. Then supply 0, ground, supply 1, VDD. So, these are basic initializations. Now, coming for this P1, PMOS primitive, P1, source, drain, gate, the terminals of the source we have to write first. So, for P1 source is at VDD. So, VDD, drain of PMOS is at out. So, comma out, and gate is at for PMOS P1 in A. Similarly, PMOS 2, P2, source is at VDD, same thing, drain is at out. The only difference is instead of in A, this will be at in B. Similarly, NMOS, N1, source, drain, gate, N1 source is wire, drain is out, and gate is in A. And as for NMOS 2, source is at ground, drain is at wire, gate is at in B. This is AND module. So, this is how we can describe a 2 input NAND gate using Verilog code. So, I will take the next universal gate, which is NOR gate. So, the connections are reverse here. Okay. So, NOR gate is here basically, this is VDD. So, in case of NAND gate, NMOS transistors are in series, P are in parallel, whereas here this is reverse, P are in series, N are in parallel. this is ground point, this is out point. This is in A, this is in B. So, we know the operation is for in A, in B, output 0 0, NOR is 0 plus 0 bar, 0 bar is 1, 0 1, 1 0 1 1. So, for any other case 1 plus anything is 1, 1 bar is 0. So, if all the inputs are 0, output should be 1. If any one of the input is 1, output should be 0. Okay. So, you can easily verify the operation similar to that of the NAND gate. Okay. So, in ideal case, if a device is on, we will take this as a short circuit, otherwise open circuit. We can verify in the similar manner. Okay. Now, if I take the Verilog code correspond to this one, we will call this one as P1, P2, similar to NAND operation. This is N1, N2. So, module I will call as CMOS NAND NOR. We have only one output and two inputs. Output, out, input in A comma in B, then we require supply 0, GND, supply 1, VDD. Then here also we require a wire, so which is not accessible to any one of these input outputs is this point. So, this is the point where this P1 and P2 are connected. This is not accessible. So, we have to define as a wire. And if you write down the source and drains of this one, these are the sources of both NMOS transistor, these are the gates, these are the drains. This is the source, gate, drain. This is again drain, sorry, this is source, gate, drain. So, if I take PMOS P1, so what is source, drain, gate, VDD, comma, drain is at wire and the input is gate is at in A. PMOS P2, source is at, for P2 source is at W, drain is at out and gate is at in B. If I take NMOS N1, source is at ground, in both the cases these are ground and drain in both the cases will be output. Gate will be, in case of N1 it is in A, in case of N2 it is in B. this end module. So, like this you can verify the Verilog code corresponding to the NOT gate, NAND gate and NOR gate, but any Boolean function can be represented in terms of this NOT, NAND and NOR gates. Okay. So, if I take example of some other Boolean function, let us take f of a b c is equal to a b plus b c plus c a. You see nothing but actually the carry of a full adder. Okay. Now, how to implement this a b plus b c plus c a? So, in order to implement using the NAND gates, I can represent this as double bar. If I take the double bar, you will get the same value. So, if I evaluate the lower one according to the De Morgan's law, P plus Q plus R bar is equal to P bar into Q bar into R bar. So, this is A B bar, B C bar, C A bar. This is one NAND gate, this is another NAND gate, this is another NAND gate, overall this is another NAND gate. Okay. So, how to implement this? So, A B is a NAND gate, B C another NAND gate, C A another NAND gate, overall you have to implement another NAND gate. So, the structure will be something like, so in the NAND we will be having this in series, for the NOR we will be having in parallel. Okay. So, I will first write down the pull down network. A B, this is B C, of course, this B and this B are same, B C, this is C A, and above this one will be, this will be in the series components will be in parallel, parallel components will be in series. Okay. This is A B, B C, C A. So, we are going to take the output here. This is VDD. So, what will be this output? Is nothing but A B plus B C plus C A whole bar. So, we have to take this output, we have to pass through the NOT gate again. Of course, these two grounds are same, this VDD is same, this is final out, which will give AB plus BC plus CA. So, to get this AB, we know that this is series, BC should be series, CA series. Okay. To get this NOR operation, they will be in parallel. Okay. So, this is the circuit diagram of f of ABC is equal to AB plus BC plus CA. You can do in other way also, you can take the NAND operation of this one, NAND of this one, NAND of this one, and then you can take the overall NAND. Okay. So, for this what will be the Verilog code? So, module CMOS Boolean expression B. We have 3 inputs, 1 output, out comma A comma B comma C, output, out, input A comma B comma C. So, now you tell me how many wires are required. So, all the points which are not accessible require a wire. Okay. So, what are the wires required? So, this point is not accessible, here I require a wire, I will define this wire as wire W1, here we require W2, W3, W4, this is VDD, this is ground, this is out, here do not require, here this C, this is A. So, this point is also wire W1, whereas here we require some W5, this is W6, and here of course this is VDD. Okay. So, total 6 wires are required. And then of course supply 0, GND, supply 1, VDD. We name this transistor total, we have 12 transistors, we call this one as P1, P2, P3, P4, P5, P6, N1, N2, N3, N4, N5, N6. So, PMOS P1. So, what is source, drain and gate? This is source, this is drain of P1 and P2, this is source, this is drain of P3 and P4, this is source, this is drain of P5 and P6. Similarly, these are the sources of N2, N4, N6. So, these are the drains, these are the sources of N1, N3, N5, these are the drains. Okay. So, for P1 source, P1 source is at VDD, drain is at W6, and gate is at A. This is for P1. Similarly, PMOS P2 source, P2 source is at VDD same, P2 drain is W6 only, but input will be B. Similarly, PMOS P3 source is at W6, drain is at W5 and gate is at B. PMOS P4 also same except for the control signal, which is gate, W6, W5, instead of B this will be C, and PMOS P5 source will be at W5, drain will be at W1, gate will be at C. PMOS, P6, P6 also same W5, W, the only difference is input is A. Then similarly 6 NMOS, NMOS N1, source of N1 is W2, drain is W1, gate is A. NMOS N2, source is same W3, W1, the only difference is instead of A, sorry, N1, N2, N2 is different, N2 is source is at ground, this will be for N3 otherwise. So, N3 will be same as N1, source drains are same, okay. So, source is at W3, drain is at W1, input is B. NMOS N5, so the source is at W4, drain is at W1, input is at C. NMOS N2, source is at ground, drain is at W2, gate is at B. NMOS N4, source is at ground, drain is at W3, gate is at C. NMOS N6, ground, W4, A. This is up to here. Then we have another NOT gate. Here also I will call this one as P7, N7. Okay. So, PMOS P7, source of P7 is, this is source, this is gate, this is drain. This is source, drain, gate. Source is at VDD, drain is at out, gate is at W1. NMOS N7, source is at ground, drain is at out, gate is at W1. This is end module. This is how you can implement any Boolean function. You can implement any Boolean function and you can write the corresponding Verilog code in this manner. Okay. So, we will discuss about this the pull up pull down networks if you do not consider the transistors in ideal case in the next lecture. Thank you.